welcome back to the healing power of nature. Today we're covering hypoxia, one of the most important causes of cellular injury. This topic is extremely high yield for USMLE Step 1 and also for practitioners because it connects basic cellular biology to clinical conditions like shock, anemia, and poisoning. We'll break it down step by step using analogies, mnemonics, and etymology to make this topic as simple and unforgettable as humanly possible. By the end of this video, you'll understand basic principles of hypoxia, causes of hypoxia, real-life scenarios, consequences of hypoxia, clinical relevance, and we'll also go through a few USMLE practice questions to help not only test your understanding, but also solidify it for the long term. Don't forget to visit thehealingpowerofnature.com for the best resources on the market. What is hypoxia? Definition: think of hypoxia as a delivery system failure. Oxygen is the package that needs to reach tissues, but the delivery system may break down in one of three ways. Today we're going to go over these three ways, but for now, think of oxygen as a package that needs to be delivered. But with hypoxia, the delivery system fails. Etymology: hypo means below, less than, normal, or insufficient. Oxia relates to oxygen, so it's insufficient oxygen. Three main mechanisms of hypoxia. First, ischemia, blocked delivery system. So blood flow is the delivery truck carrying oxygen to the tissues. Ischemia is like a traffic jam. No deliveries are getting through. So some common examples are atherosclerosis, which is where plaque blocks arteries, causing a heart attack or stroke. Another common example is venous blockage. Blood gets trapped in the liver, like in Budd-Chiari syndrome. Shock, low blood pressure stops oxygen from reaching tissue system-wide. Hypoxemia, recognize it's not hypoxia, but it's hypoxemia. Hypo means below, emia means blood, so it's low oxygen in the blood. Imagine trying to fill up your car at the gas station with no gas in the tanks. Hypoxemia is like running out of oxygen at the source. So some common examples that are high altitude, there's less oxygen in the air, which means there's less oxygen in the blood. Lung diseases like COPD or pulmonary edema impair oxygen exchange in the lungs. Diffusion block as well in conditions like pulmonary fibrosis, thickened walls in the lungs slow oxygen exchange, much like trying to pass a note through a thick glass wall. Remember, hypoxemia leads to decreased pSmall-a O2, while ischemia doesn't necessarily. Decreased oxygen carrying capacity. Hemoglobin is the truck that's carrying the oxygen. If the truck breaks down, oxygen never reaches the tissues. So examples of this are anemia. Anemia is fewer red blood cells or hemoglobin, which means less oxygen transport. Another common example that is highly tested is carbon monoxide poisoning. Carbon monoxide binds to hemoglobin with 200 times more affinity than oxygen, effectively blocking oxygen delivery. Mnemonic you can use is CO is the cruel opponent. Another high-yield example would be methemoglobinemia. Hemoglobin oxidizes from Fe2 to Fe3, which can't bind to oxygen. The big clue with methemoglobinemia is chocolate-colored blood and cyanosis, commonly caused by drugs like nitrites. So, key consequences of hypoxia. First, the sodium-potassium pump failure. ATP depletion, because it requires ATP to function, causes sodium to influx in the cell to swell. The reason why the cell swells is because as sodium enters the cell, osmosis happens and the water follows the sodium. Another one is lactic acidosis. Anaerobic glycolysis produces lactic acid, which lowers the pH and in consequence damages proteins and DNA. Most importantly, membrane damaged. So prolonged hypoxia causes membrane rupture and leakage of essential enzymes, which we can test for in different tests, but it's once the membrane is damaged, it is now irreversible injury. Some high-yield real-life scenarios. There's one would be atherosclerosis. This is a highway blockage. So in atherosclerosis, fatty plaques build up in the walls of arteries, reducing or completely blocking blood flow. Since blood is the vehicle that delivers oxygen to tissues, this blockage causes ischemia, restricted blood flow, and leads to hypoxia, which is oxygen deprivation in tissues. So for example, a heart. When this happens in the coronary arteries, the heart muscle is deprived of oxygen, leading to myocardial infarction or a heart attack. In the brain, with the cerebral arteries, this results in a stroke. Imagine, for example, a highway carrying food trucks. blood-carrying oxygen to a big festival, the heart. Over time, construction debris or atherosclerotic plaques narrows the road, eventually creating a complete blockage. No trucks can reach the festival, and the event has to shut down, just like oxygen-deprived heart cells that die during a heart attack. Next, a very, very common example is carbon monoxide poisoning, like we talked about. What happens is hemoglobin, the protein in the red blood cells, is like an elevator that's designed to carry oxygen to tissues. Normally, each hemoglobin molecule can bind 4 oxygen molecules. However, carbon monoxide has a 200 times more affinity for hemoglobin compared to oxygen. Once carbon monoxide binds to hemoglobin, it blocks oxygen from binding and being transported. This leaves tissues starving for oxygen despite normal oxygen levels in the lungs. So symptoms of this include headache, dizziness, confusion, and most importantly, cherry red skin. Picture an elevator with a space for 4 oxygen passengers. CO acts like a pushy stranger who enters the elevator and occupies all the available spots. Now the elevator can no longer transport oxygen to the upper floors or the tissues. The tissues become hypoxic and begin to fail. Next, shock is a condition where the delivery of oxygen and nutrients to tissues is insufficient due to systemic issues such as low blood pressure or poor cardiac output. This can be caused by a few different reasons. First, hypovolemic shock, which is low blood volume, common in massive bleeding scenarios. Cardiogenic shock, which is a heart failure or myocardial infarction. Septic shock, which is widespread infection causing blood vessels to dilate and leak. Shock leads to a critical lack of oxygen and nutrients, impairing cellular function and eventually causing widespread organ failure. Imagine a city where the electricity, being oxygen, powers all the homes, which could be the tissues. During a power outage like shock, electricity is cut off from the entire city and everything comes to a standstill. No lights, no air conditioning, no functioning appliances. Similarly, tissues deprived of oxygen in a shock can no longer perform vital functions, leading to cellular injury and death. Additional clinical correlations. Stroke. Neurons are highly sensitive to hypoxia and undergo irreversible injury within 3 to 5 minutes. Most affected region is the hippocampus, CA1, and Purkinje cells in the cerebellum. Myocardial infarction. Cardiomyocytes die after 20 to 30 minutes of ischemia, leading to coagulative necrosis. Most vulnerable region is the subendocardium. Acute tubular necrosis, or ATN, renal tubular epithelial cells are highly sensitive to hypoxia due to their energy demands for ion transport. Methemoglobinemia, common tested drug abuse condition. This is often treated with methylene blue, which restores Fe2 from Fe3. So it restores Fe2 to bind oxygen. Interestingly enough, methylene blue is actually a dye that was used industrially. Some key mnemonics can really help you understand hypoxia. My favorite one, I hate low oxygen delivery. I representing ischemia, H representing a hypoxemia, L representing low oxygen carrying capacity, O for obstruction or vascular or airway, D for diffuse defects. Coal can be used as a key cause of decreased O2 carrying capacity. C, carbon monoxide, like we talked about. O, oxidized hemoglobin, also known as methemoglobinemia. A, anemia. L, low red blood cell count. Now, let's go ahead and jump into some practice questions to help you solidify your knowledge. Like I will always tell you, start with the bottom, then read your question answers, then read the entire answer. Okay, if you chose B, hippocampus, CA1 region, you are correct. For the explanation, the hippocampus, particularly the CA1 region, is highly sensitive to hypoxia due to its high metabolic demand. In ischemic stroke, neurons in this region are often the first to undergo irreversible damage. Other vulnerable areas include the Purkinje cells in the cerebellum and layers 3, 5, and 6 of the cerebral cortex. Let's go on to our second question. All right, if you chose C, you are correct. So remember, carbon monoxide binds to hemoglobin with 200 times the affinity of oxygen, which prevents oxygen transport to tissues. Lastly, we'll do one more question. If you chose B, the proximal tubule, you are correct. The proximal tubule is the most metabolically active segment of the nephron, requiring large amounts of ATP for active transport. During ischemia, hypovolemic shock, the proximal tubules are highly susceptible to hypoxic injury, leading to acute tubular necrosis. Good job. That concludes our video for today. If you found this helpful, please visit thehealingpowerofnature.com for the best study materials on the market. Thank you very much. See you next time.